what did we do last week? Last week we did some proofs of properties of continuity. We looked at theorems 4.3 and 4.4, which told us how continuity meshed well with the fundamental operations that we can do with real-valued functions, namely adding functions together, taking linear combinations, multiplying functions together, taking quotients, and so on. And also then the very important operation of composition, applying one function after another one. So theorems 4.3 and 4.4, we did the proofs for most of the parts of 4.3. They tell us how the concept of continuity fits very well with these operations. So having done that preparatory work, then we're ready now to move on to the definition of the derivative. Now there's some remarks in the notes and some diagrams in the notes, but I think I'll switch to the overhead just to give the introduction. So I'll be saying most of the points here that are in the notes, and also making some additional remarks here. Okay. So we are talking here about the derivative of a function, of a real-valued function defined on the real numbers. So typically we're talking about function f from R to R. It's also applicable to functions which maybe aren't defined on the whole of the real numbers, where the domain is some subset of the real numbers. It applies equally well to those, but at the moment we'll just assume that the domain of the function is indeed the whole of the real numbers. Okay? This is a function taking values in the real numbers as well. So such functions, of course, can be thought of in terms of their graphs. So you can have an x-axis and a y-axis, and then this graph here is the graph of the function y equals f of x. Now what the derivative is, so just in one sentence, the derivative of a function is a quantity that you can attach to any point in the domain, and the derivative tells you how fast the function is changing at that point, or what the rate of change of a function, the rate of change of f at a single point. Let's for the moment just call this A, a single point, x equals A in its domain. Okay, in one kind of sentence, that's what the derivative is. Now, why is this useful? Well, it is indeed incredibly useful. I mean, it's one thing to know the value of a function at a particular point. That tells you a lot about the function, perhaps the most important aspect of a function at a particular point, what the value is. So this value, so this point A here, talking about this value over there on the y-axis, the height at that point. But of course, there is an infinite collection of functions which take the same value at A, and all of them would look very different from this function here. Okay? So the value of a function at a particular point is only really just the first piece of information you have about the function. What tells you more information then is how fast the function is changing at that point. Is the function increasing as you go through that point A in the domain, or is it decreasing, and so on? And then further, you could ask, well, what is the rate of change of the rate of change? Is the function accelerating at this point? Is it increasing and increasing faster as you move to this point? Or is it increasing and the rate of increase is itself decreasing as you move through? There's all these different questions you can ask, and then you can even take it one step further. You could ask, well, what's happening to the rate of change at the rate of change? Is it getting fast? Is it increasing at this point? Is its rate of increase increasing? And is that rate of increase itself increasing? So those kind of, what I'm referring to there is the first derivative and the second derivative and the higher order derivatives of the function at a single point. And when you look at the discipline of applied mathematics or mathematical modeling of problems in the real world, engineering and physics problems or problems in any field of science, in the most frequent type of setup that you end up looking at is you end up looking at differential equations. Okay? There'll be some function or functions which are measuring important aspects of your model, and under the scientific laws, whether they be laws of motion of physical bodies, or chemical laws about the speed at which reactions happen and so on, oftentimes, whatever the scientific principles or laws are, when you impose those on the model, they give rise to differential equations. Okay? Equations featuring the description functions and their derivatives. Okay? And one sentence definition of what mathematical modeling is kind of setting up these differential equations and solving them. And many of some of the important second-year courses and third-year courses in your degree are concerned with the study of how to solve differential equations. Okay? That lies at the heart of a lot, or the majority of mathematical modeling of problems in engineering and physics anyway. So we're kind of at the start of it here. I'd like to talk about the definition of the derivative of a one variable function. Okay, but first we introduce the notion of the change. First, we're going to consider the change in behavior, the change in value of f between x equals a, or between a and a nearby point x. So I'll do a sketch of what I mean. So here's our function. Here's our base point A, and here is a second point x, which is somewhat close to A. So here's the value of the function f at the point A, the height at this point. You've got f of A, and you've got f of x, then the height of this. The height of the value of the function at x. So we can talk about the change in value of f, and that would be equal to this quantity f of x minus f of a. That's the distance between these 2 points on the y-axis. Okay, f of x minus f of a. But now, we ask ourselves, is that a good quantity to look at? Or might there be a slightly better quantity to look at? Because we're interested in getting to the notion of the rate of change of the function at the point A itself. So first of all, we're just assuming that we're considering it between the point A and some other nearby. But now this difference might turn out to be large, or it might turn out to be small. But even if this difference turned out to be large, it doesn't necessarily mean the function is increasing very fast or decreasing very fast, because it could be that the point x is quite far away from A. So even though the function might only be increasing very slowly, if x is a long way away from a, then you might observe a large difference in values. Whereas if this difference was very, very small, the function could still be increasing very rapidly if your nearby point x itself was extremely close to a. So it's not so much the absolute change in value that is a good measure of what's going on with the function between these 2 points, but rather the relative change in value. So the relative change in value would be the absolute change in value that you see relative to the change in value of the argument, okay? Or expressed as a proportion of the change in value of the argument. Okay? So that would be this quantity here, where we divide the absolute change in value, f of x minus f of a, divide that by the change in value of the argument to the function. So f of x minus f of a is a measure of that distance there. X minus a is a measure of this distance here. So this distance here is x minus a. This distance here is f of x minus f of a. And these are signed distances. They carry a plus or minus sign depending on whether f of x is bigger than f of a and whether x is bigger than a and so on. And there's a nice geometric interpretation that we can give to this relative change in value. The relative change in value will actually be the slope of this line, this sometimes called a chord of the graph, defined at these 2 points a and x. And this relative change in value also is the gradient or slope of this line L, which I've drawn against C. Which I've drawn on the graph. Okay, so this straight line which joins the 2 points A, f of a, and x, f of a. So this line is a kind of first order description of the change in value, or what's happening to the function between these 2 points. Okay? So this gives us the relative change in value of the function f between points x and a. Between points x and a. Now, if we're interested in capturing the instantaneous rate of change, there's a clear process that we can go through to get closer and closer to the instantaneous rate of change. If we keep the value a fixed, so a is a fixed point in this discussion. But if we let the position of our nearby point x, if we bring that closer to a, then we're going to be looking at the relative change in value of the function across much smaller ranges. Okay? And if we send x closer still to the point a, you'll be looking at the relative change in value of the function across an even smaller interval. And then the theory we've built up to now, when we looked at sequences, series, functions, we talked about the limiting values of these objects. So this gives us the definition of the derivative. So considering this relative change, in f as x gets closer, let's say closer and closer, so that reminds us of the phrase we used to describe this idea of convergence before we met the formal definitions involving epsilons, points and sequences, and deltas and so on. So we consider this relative change in f as x gets closer and closer to a. Considering this gives us the definition of the derivative. So this is the definition in 4.3. So the derivative of f at x equals a is the limit, this limit here, which is the limit as x approaches a of this relative change in value of the function. So this is what we call the derivative. Now there's various notations for these, but the two kind of main notations we're going to make use of. Notations for this. And the most traditional one is to talk about this notation df dx. So this represents the derivative of the function f with respect to the variable x. So the variable x is included in the notation. And you might also put an evaluation line beside it, a subscript there, to say that we're talking about the derivative of the function at this specific point, x equals a. But another common notation, a more compact notation, is the dash notation, where you just have the function letter with a small dash beside it, and you also indicate the position that you're talking about, where you're taking the derivative, as being at the point A. Okay, so these are two different notations for the derivative, and different authors have different preferences, and in different subjects or different subject disciplines, there might be slightly different traditions or conventions about which notation is preferred, but they're both equally valid. In this one, using the dash is obviously more compact and is typically would have the same height as the surrounding text in terms of when you're writing out stuff or typesetting mathematics, whereas this df dx, this kind of fractional thing, typically would come out taller in the line, so there's typesetting considerations if you're designing a book with mathematics in it and so on. But the df dx notation does have a slight advantage in that it allows you, the first notation, let's say, first notation allows us to write the derivative as d dx applied to a function f. So it allows us to think of the process of differentiation as a thing in itself, as an operator in itself, or a kind of a function, if you like, which takes as an argument another function and the position A, I guess. So it allows us to write things like this, which shows differentiation as an operator applied to a function f. And you can refer to the operator itself as ddx. You can refer to the process. You can name the process with its own name. You can talk about it. Whereas this notation, the f prime. So in English, if you were reading this, you might read this as the derivative of f. Of course, this type of notation is used in other areas of mathematics. It can be just a general notation to refer to some object related to f. So if you've got some object f you're looking at, when you put a prime or a dash beside it, so if you're reading this, you can also read it as f prime. And in other areas of mathematics, that might mean just some other object, but an object related to f. So you want to use the letter f. You use the prime to indicate that, well, it's not exactly f, but something related to f. Okay. But in the context of calculus, that would typically refer to the derivative of f. And while it's nice and compact, it's not so easy to see the differentiation as a separate operator in and of itself, because this prime notation, I mean, it's difficult to talk just about a disembodied prime, or just this prime dash notation in isolation of any other letter that it's attached to. That's just a bit more, whereas this DDX notation is a bit more substantial to use as an operator. Okay, so if this, of course, the other aspect about limits is, of course, that they don't necessarily exist. We've seen plenty of situations, sequences, series, and functions where there is no limiting value. So derivatives for functions don't necessarily exist, but if they do, so if this limit exists, then it's referred to as the derivative of the function f at a. Before we look at some examples, it might be instructed to just show a couple of reasons why the derivative might not exist. Okay. So this limit, of course, might not exist. So here's a couple of situations where it might not exist. And if the function f is not continuous at a, so, I mean, one typical kind of picture for that is where the function a makes a discontinuous jump in value at the point a. And maybe the function has as its value at a, maybe it has this lower value, is the actual value defined at a. But then for all points bigger than a, it's taking values on this upper branch here. Well, there's a problem here with defining the derivative at a, because if you take the limit as x approaches a from the left, you would end up with this limiting line here. Whereas if you took the limit as x approaches a from the right, what would be the limiting line? What would be the limiting line, this tangent line, if our other point x approached a but from the right? Well, that would produce the limiting line to be the straight vertical line here. Okay, so as x got closer and closer to a from a point on the right, these chord lines, as x got closer and closer to a, would be looking like these vertical lines here. As x was here, and x was here, and as x is approaching a, the limiting value is going to be this vertical line. Of course, those lines have infinite slope. A vertical line has infinite slope. Okay? So the value of this, or this limit, if you were considering this function and letting x approach a from the right, this limit wouldn't exist. It would be unbounded, or would be equal to the value infinity. Okay? So if the function is not continuous at the point a, that can cause a problem. The derivative of the function might not exist. The second reason is that even if f is continuous at a, its rate of change might not be. So here's our function coming along here, but suppose then it does something like this. So at this point a, now there's something curious going on there. There seems to be a very sharp point in the function, there. And again, there seems to be two different limiting lines here, or tangent lines. If you're approaching a from the left, the chord lines seem to settle down in a limiting sense to this line here, whereas if you approach a from the right, you've got this steep line here. So again, the limit doesn't exist. It's ambiguous. It depends how you approach the point A, whether you approach it from one side only, and then it makes a difference from which side you're approaching. Okay? So such a function as it's sketched here, such a function has two derivatives, you could say. Now we won't formally set this up and deal with this in a kind of rigorous way, but you can do it. A left-handed one and a right-handed one. Okay, so you get a different limiting value for the relative change value of this function, depending on whether you approach it from the right, in which case it would be the gradient of this line here, or whether you approach it from the left, which would be the gradient of this line here on the left. So this would be the right-handed tangent line, and this would be the left-handed. But this kind of behavior, both of these kinds of behavior we kind of consider to be kind of bad behavior for a function at a point. Not being continuous at the point and making a sudden, having its rate of change not being continuous. These points in kind of deeper analysis or more general mathematical analysis, these points are referred to as points where the function isn't smooth. Okay? So our original sketches of our nice, continuously changing, evenly changing function, these are termed, there's a technical term you can set up, is that these are smooth. If the derivative of the function exists everywhere, then it's smooth everywhere. Whereas this point here, this sharp point on the function, is a point where the function is not smooth, where the derivative does not exist. Okay. So let's now look at a few examples of working with the definition. So these are examples of taking relatively simple or easily understood functions and working out what their derivatives might be. Okay, so we're going to look at functions defined by polynomial terms. Okay. So these examples are discussed there in the notes, but I'll just talk through them on the page again. So consider the function defined by this equation here. F of x is equal to k times x for some k, some constant k. Okay, so it's a relatively simple function. This is just a function whose graph is going to be a line that goes to the origin. Okay, y equals k of x is the equation of the line going through the origin. And then for any a in the domain R, the derivative of this function evaluated at a, well, by the definition, it's the limiting value as x approaches a of the relative change. So we can just put down the definition. So this expression here, remember, is the relative change in value of the function. The change in value, which is the top, f of x minus f of a, but relative to the change in the argument, which is x minus a on the bottom. And we're taking the limit of that as x approaches a. So the next step would be, well, actually putting in the definition of the function. This is kx minus k times a, all over x minus a. So now this is a limit which we seek to evaluate. Of course, there's a problem in you can't evaluate it just by substituting in the limiting value x for a. If you do that, you have a 0 over 0 fraction, which isn't defined. But if you look a bit closer, of course, you see that the fraction can be rewritten in such a way as to show that it can be simplified. Okay, you can factor out the k, and suddenly you're looking at k times x minus a over x minus a. Now, at every point except at A, this quantity is, of course, equal to k, because you can just cancel the x minus a from the top and bottom. Remember, the limiting value process doesn't refer to the value of this quantity actually at x equals a. It's just referring to its limiting behavior as x gets closer and closer to a. So in this limiting process, x is never actually equal to a, but there's nothing to stop us cancelling that factor x minus a from the top and the bottom. Okay? The x minus a is never itself equal to 0 in this limiting process. It gets arbitrarily close to 0, but it's never actually equal to 0. So we can cancel it from the top and bottom. So we'd just be looking at the limiting value of the constant k. So it's cancelling x minus a, which is, of course, equal to k. This k is just some fixed constant. Its value doesn't change as you change x. So we're just left with the limiting value k. So you see here that the derivative of this function doesn't depend on the value a. There's no a here in the answer. So it has the same derivative everywhere. Okay? So this is a function with constant derivative. Now this function was a line, it's just a straight line of gradient k, and so of course the tangent, so it's nice, it's kind of fitting that the tangent line to such a graph also has gradient k as well. Now we can, so there's another example which is shown there, which is the function x squared. Okay, so new function now, f of x equals x squared. Well, in a similar way, we can obtain the derivative of f evaluated at a point A. The limiting value as x goes to a of the relative change, as before. It's just the definition. And then putting in the definition of the function, we now have x squared minus a squared over x minus a. The first line is just the definition, the limiting value of the relative change in f. And we then have the limiting value of putting in the definition of f. Again, there's a problem here with calculating the limit just by substituting x equals a, because again you'd have the 0 over 0 thing. But of course here, we can again factor the x minus a, because the top factorizes as x minus a times x plus a. That's divided by x minus a. So the x minus a's will cancel out with each other, so we'll just be looking at the limit of x plus a. X tends to a. Now this is a nice continuous function, x plus a. So its limiting value as x approaches a is we just substitute a for x, and we get the quantity 2a. A plus a, 2 times. Okay, so here the value of the derivative does depend on where you're evaluating, okay, because there is an a in the answer. Okay. Maybe I'll just switch back to the notes for a moment. Just while I'm letting people get that down, are there any queries at this point, or any clarification that I could provide on any of that for you? Okay. Now, so we've worked through those examples. Now we'll be spending a fair bit of time with the derivative. there's lots of properties of the derivative to explore, and lots of theorems, well, not lots, but a few theorems about it which we'd like to prove. So we'll just take a little bit of a look ahead at what's to come then. But those examples we've been talking about, and in that definition, we're just talking about the derivative, or what's also called the first derivative of the function. But as I said in my introductory remarks, you can, as well as considering the rate of change of a function, you can also consider, well, what's the rate of change of the rate of change? In an economic, in another setting to illustrate that, so people talk about. So looking at the economy, people talk about the price of a certain good. That's the first measure of what's going on with the value of the good. What's the cost of the good? Of course, over time, you look at the historical record and prediction into the future, the price of the good might be changing. That's referred to in economics as inflation. Okay? You either have positive inflation or negative inflation. Positive inflation is the prices of goods increasing. Negative inflation is the price of goods decreasing. But then another important measure of what's going on in the economic model is what's happening to the rate of change of inflation. Is inflation increasing or inflation decreasing? Is the rate of change of the cost, is that rate of change itself increasing or decreasing? So that's referring to a second order derivative, the rate of change of the rate of change. So here, this notation here, d2f dx squared, is how you'd read it in English. That's referring to the first derivative of the first derivative. And here you see the advantage of this notation here. And the ddx notation, as you can easily see, or it allows you to view the process of differentiation as an operator applied to a function. So d2f dx squared represents the derivative of the derivative. Okay. And then you can go higher order as well. Look at the third derivative, fourth derivative, etc. Okay. Now, those examples we just went through a moment ago were examples where we took some standard functions, the function f of x equals x and f of x equals x squared, and worked the limit definition in order to derive their derivatives. And we will do that with some more functions, but in a more practical day-to-day case, we'll want to be making frequent use of results about the derivatives of standard functions. So on the next page in the notes, there's an extract here from the standard mathematical formula book that we use, and that you'll have available in examinations and so on. So this is an extract here. So here you've got a family of standard functions down the middle of the page, and to the right you've got their derivatives. And to the left, you've got their integrals, which Saeed will have been talking about with you. So you can see here we've got one family of functions, x to the power n. So that would cover the two examples we've just looked at. X to the, where n is equal to 1 and n equal to 2, at the two examples we just looked at. And over on the right-hand side, you've got the formula for the derivative. Okay, that familiar formula where you take down the index and decrease the index by 1 and so on. Okay, and you got a whole other bunch of standard functions, logarithm, exponentials, trigonometric functions, hyperbolic functions, and so on, and then these other functions involving square roots and so on. And a few more over the page. Then you've also got, so this is the second page of that extract from the formula handbook. You've also got various properties of differentiation listed there. And those properties are introduced on the next page in the notes. So these, we're going to concern ourselves with looking at these and looking at the motivation for and explanations of these and various applications of them in the coming lectures. Now, it won't surprise you, you've seen it mentioned looking at sequences and series and limiting values of functions and continuity. You've seen this word linearity crop up all the time. And in your study of vectors and matrices, you're studying linear algebra in one of your other units. So this notion of linearity is a very important notion that lies across a lot of mathematics. So it won't surprise you to see it appear here. The first result about the derivative, the first general result about the derivative we're going to prove is that it's a linear operator. So what does that mean in this context? Well, in this context, that means if you've got two functions, g and h, well, you can take a linear combination of them to form a new function f. The f is alpha times g plus beta times h. Alpha and beta are two real coefficients. And here you've used the functions g and h to form a new function f. And the question is, well, what is the derivative of f? How does the derivative of f relate to the derivatives of g and h? Well, it relates in a very nice way, in an exactly linear way. The derivative of this function f will be alpha times the derivative of g plus beta times the derivative of h. That's saying that the derivative operator is a linear operator. Then you've got another property called the product rule relating to products of functions. You've got a chain rule relating to compositions of functions. There will be a quotient rule relating to quotients of functions, and so on. Okay, so these are familiar concepts that we've looked at in our previous work on convergence and limiting values of various objects. We'll be looking at these again for differentiation. Now, some of those, for a lot of you, those properties will be familiar. You looked at those in A-levels or in your previous study of mathematics, so they'll be familiar to you in one sense, but we will be giving what you mightn't have seen before is rigorous proofs of them from first principles, using the underlying precise notions of convergence and limiting values. Okay? So that's some of the things we'll be concerned with in the coming lectures. So my next lecture with you will quickly review this definition, and we'll continue on then with the linearity and product rule and so on. Okay? And in terms of the tutorials this week, so Frank is still off, unfortunately, so for Frank's Mathematics Fundamentals tutorial tomorrow, I'll be covering that. So still come along if you're in Frank's class, his tutorial tomorrow. Just for the tutorials, there are, I think now is open to you questions 1 to 4. Questions 1 to 4 on page 55. So we'll be looking at those tomorrow.